Hello everyone, I hope you're all doing well. We're now going to start with Unit 1-4 of our course lectures. Unit 1-4 will be focusing on single factor experiments. We will have 2 lecture videos for this unit. Part 1 will be devoted to the fixed effect model, and then in part 2 we're going to tackle extensions of the discussion in part 1, where we're going to talk about random effect model, randomized complete block design, Latin square, and the Greco-Latin square. I hope you'll be able to learn a lot from the following 2 videos, and I encourage you to always, again, check your ouvlet and look at the worked out examples that we will be discussing on in the lecture videos. I'll be posting the R codes, the data as usual, and always make sure that you try to answer the review questions and look at the concept checkpoints that I will be posting. All right, happy learning. Welcome back, everyone. This is Dr. MAMTamayao-Kieke, and this is the first lecture under Unit 1-4 on single factor experiments or analysis of variance. So for today's topics, we're going to tackle the following objectives. First of all, I want you to be able to understand the fixed effect model by the end of this lecture video, and then to be able to perform analysis of variance, and in particular calculate sum of squares, because you'll be needing these sum of squares for the ANOVA table. And then for you to be able to perform model adequacy checking and recall why you have to do this. And then lastly, of course, with the results of your ANOVA analysis, that you will be able to interpret the results. But before we go into the topics, let's first have a review question. True or false? In an experiment where the objective is to compare the performance of 2 populations, 25 unpaired observations were made. The variance of the population's performance is not predetermined and cannot be assumed to be equal. In conducting a hypothesis test, the t-distribution can be assumed for the test statistic. All right, true or false? So the answer to this is, the statement is true. All right, so I'd like you to be able to identify the specific type of distribution and the type of test that you can employ whenever you are given a problem where you have to compare the performance of 2 populations. All right, now getting into our topic for this lecture. So we have been living in a highly digital and interconnected world even before the pandemic started. But the COVID-19 pandemic actually pushed our societies to become even more dependent on the advantages of a digital and smart systems. So products like your smartphones, your computers that enable this transformation are now seen as commodities. Okay. And one essential part of these products is the integrated circuit, and this is the subject of our class example for today's topic. Actually, the example focuses on this thing. Okay. The example focuses on plasma etching on wafers, which is an integral component of the fabrication of integrated circuits. And we will be using this example in our discussion on single factor experiments or analysis of variance, specifically for the fixed effect model. So let's look at the example. This is a problem. An engineer is interested in investigating the relationship between the RF power setting and the etch rate for this tool, the tool for the plasma etching. The objective of an experiment like this is to model the relationship between etch rate and the RF power, and to specify the power setting that will give a desired target etch rate. Now, the engineer is interested in a particular gas and gap and wants to test 4 levels of RF power: 160, 180, 200, and 220 watts. She decided to test 5 wafers at each level of RF power. So, question: can we use any of the tests we've discussed so far? What do you think? Alright, so to help you answer this, how many factors, you have to be able to identify how many factors did we deal with in our previous tools? You're right. We only dealt with 1 factor. Now, how many levels per factor? Again, you're right. We only dealt with 2 levels so far. Now, in this experiment, okay, you can see here that we also have 1 factor, and that is what? You have RF power. Okay. However, instead of having just 2, we have 4 factors. Okay, or we have factor levels, and we have 4 treatments. Okay, so to answer this, we actually cannot use any of the tools that we have discussed so far in an efficient way. I mean, of course, we can use them, okay, but there is a more effective and efficient tool in our statistical analysis toolbox that we can employ in this particular example, where we have 1 factor and more than 2 treatments, or more than 2 factor levels. Okay, so in the case where we are dealing with 1 factor, okay, and more than 2 levels, what we can use is the one-way analysis of variance. So again, in our plasma etching example, our dependent variable is the etch rate in angstrom per minute. And then we have 1 factor, that is the RF power in watts. And as we mentioned, we have 4 treatment levels, okay? And we usually denote, well, in this lecture, we're going to denote treatment level or treatment as A, and we have 4, so A equals 4. So these are the levels. And then we have 5 replicates for each treatment. So we denote replicate as N, and N is equal to 5. Therefore, our total number of observations is equal to a capital N, which is equal to A times N. So that's 4 times 5 equals 20. Now, before we proceed to the actual ANOVA, the fixed effect model and the ANOVA table, I'd like to first remind you to always remember that one of the most important parts is your planning and the actual design of your experiment. And one important step in this is identifying your test sequence. Okay, so remember to always randomize the test sequence. Okay, and what you can do here is you can you have your total number of observations, and then you can generate your random numbers in Excel, for example. Okay, and you can list the different levels beside your randomly generated numbers, and then you can just sort the random numbers from lowest to highest or highest to lowest, so that you can have the corresponding treatments also randomized. Okay, so you can follow that sequence in implementing your experiment, and I can upload an example done in Excel on Outlier. But I'm sure you can do that easily on your own. In any case, so let's go back to the experiment, the plasma etching experiment data. Okay, so we have here, say the engineer followed our test sequence and was able to gather the following data for the plasma etching experiment. Okay, so again, we have 4 treatments, and we have 5 replicates for each treatment, making 20 observations all in all. All right. Now, this set of data in the setup for a one-way ANOVA can actually be generalized in this way. All right. So you have a single factor, you have A treatments, okay, or factor levels, and then you have N observations or N replicates for each treatment, okay, making A times N observations. All right. Now, what is the difference between a balanced and an unbalanced design? So basically, in a balanced design, you have equal n, small n, for all the treatments, okay, for all the factor levels. In an unbalanced design, okay, the number of observations per treatment level will not be equal. Okay, so that's the only thing that you have to remember regarding the differentiation between balanced and unbalanced design. And of course, correspondingly, the model will vary a little bit. Okay, but let's first focus on this experiment where we have a balanced design. Okay, before we do any statistical analysis, we first look at a graphical analysis, which is still part of statistical analysis, but I mean the numerical part. No, let's first. It's good practice to always start with a graphical analysis. Okay, and one simple yet powerful tool that we can always use is the Boxplot. Okay, and this is the Boxplot generated in R, okay, for our plasma etching experiment. And from this Boxplot, what can you say? It appears that if you just look at this Boxplot, that there seems to be a difference in the etching speed for different power levels. And the other thing that you can probably observe is that as you have you increase your power level, the etching speed also increases. Okay. However, in some cases, these kinds of patterns are not very apparent. Okay, and for us to be able to perform a more objective analysis, we use ANOVA. Okay, but before we go into the ANOVA table, which is actually the easy part, okay, let's first understand the model, the statistical model behind it. Okay, now remember your means model. Okay, we used this in our previous tools. Okay, the means model can be used to actually represent our data. Okay, and here you have y sub ij, okay, equals mu sub I plus epsilon ij. Okay, from I equals for I equals 1 to A and j equals 1 to n, where your y sub ij is your jth observation for the ith treatment, and your mu sub I is the mean for treatment I, and epsilon ij is the error for the jth observation in the ith treatment. Okay. Now, this means model can actually be transformed to the effects model. Okay, so how do we do that? We can actually represent mu sub I to be equal to mu plus tau sub I, from where I is equal to 1 to A, and mu here is the overall mean of the observations, and tau sub I is the mean effect of each treatment I. So it's the mean deviation, okay, associated with treatment I from the overall mean, and this is equivalent to your mu sub I. And take note, if you get the sum of all your treatments, okay, then it should be equal to 0 for this to be true. Now, given this, you can rewrite your means model to the effects model. This is now our effects model, to y sub ij equals mu plus tau I plus epsilon ij. Okay, and of course, let us remember that the assumption here is that our y sub ij is normally distributed with the mean mu plus tau sub I and variance sigma squared. Okay, so also take note that in the fixed effects model, we actually chose the treatments. Okay, we chose the factor levels. The experimenter specifically chooses the factor levels. Okay, and therefore the conclusions that you will be able to derive from the fixed effects model and the corresponding analysis are going to be applicable only to the treatments that were considered. Okay. Now, this process that we discussed last time is actually going to be still applicable here because essentially we're still going to be testing hypothesis. All right. So remember, we have to know what parameter we're interested in. We have to be able to state our H naught in H1, our null and alternative hypothesis. Identify our acceptable alpha and beta. Determine what proper suitable test statistic to use. And then, of course, determine the critical region, compute for the corresponding values, and determine whether to reject your null hypothesis. Okay? So again, I'd like to emphasize, you can actually use the previous tools, for example, the t-test in this case. However, you're going to have to, as you will see in the next slide, okay, you're going to have to implement 6 t-tests for this particular experiment. Okay, so aside from being less efficient, it will also actually compromise our type 1 error. Okay, so that's why in this case, where we have one factor and more than 2 treatments, we prefer to use the ANOVA, okay, one-way ANOVA. And in this case, of course, we're interested in our means, right? The means for the different treatments. And our null hypothesis would be that all the treatment means would be equal. Okay? And the alternative is that at least one pair is not equal. Okay? And since, you know, we in the previous slides, we already presented the fixed effects model. We know that mu I is equal to mu plus tau I, right? And the summation of mu I from I equals 1 to A divided by A is just equal to mu. And we also said that the summation of all your tau sub I from I equals 1 to A is equal to 0. Therefore, we can actually rewrite our null and alternative hypothesis corresponding to the fixed effect model to this. Okay, so basically we're testing for the mean effect of the different treatments. That's why it's called the fixed effect model. Okay, and fixed because we have identified the specific treatments that we want to investigate. All right, so let's go through the rest of the process. So we've already identified this. So say we're looking at alpha equals 0.05. Okay. Now let's look at what test statistic we should be using. Now, in this case, the test statistic that is relevant is derived from the F distribution, okay, because it could be expressed in this expression. F naught is equal to sum of squares of the treatments divided by A minus 1, which is actually the degrees of freedom for the treatments, all over the sum of squares for the error divided by the total number of observations minus the number of treatments, which is this one is the degrees of freedom for your error. And this is also equal to MS treatments divided by MSE. So MS treatments is basically equal to this, and MSE is basically equal to this. All right. And we're looking at degrees of freedom A-1 and AN-A for our test statistic. Okay, now that we know the test statistic, let's look at the critical region. So this is the critical region. It's basically the area where your F0, your test statistic, is greater than this parameter, which is F of alpha with degrees of freedom A-1 and capital N-1. Okay. Of course, alternatively, you can use the p-value approach. Now, this is how you compute the sum of squares for a balanced design. Okay. Note that your total sum of squares is equal to your treatment sum of squares and your error sum of squares. Now, to compute for your total sum of squares, this is the formula that you can use. And for your treatment sum of squares, this is the formula that you can use. To get your SSE, your sum of squares for your errors, you just subtract the treatment sum of squares from the total sum of squares. For your unbalanced design, it changes a little bit, okay, from your SST here. The difference is mainly in the treatments computation for your sum of squares. Okay, as you can see here, the first expression, which is summation of yi dot squared over ni from I equals 1 to a, compare that to, okay, so 1 over n here is outside because here n is basically the same for all your treatments. All right. So now this is one of the most useful tables that you will be using in this course, the ANOVA table. The ANOVA table basically summarizes the sum of squares, the degrees of freedom, the mean square for each of the sources of variation in your model, as well as the test statistic. In the first case, in the fixed effect model that we have talked about so far, using one-way ANOVA, you have three sources of variation. You have between treatments, you have within treatments or the error, and of course you have the total, which is the sum of the between treatment and within treatment. So we denote the sum of square of the errors or the variation for between treatments as SS treatment, and for the error as SSE, and for the total SST. And these are the corresponding degrees of freedom: n-1 for the treatment, capital N-A for the error, and capital N-1 for the total. This is how you compute the mean square for the treatment and the error, or we also call it residual, respectively. So you can see a pattern. In the numerator, you have the sum of square, the corresponding sum of square. In the denominator, you have the corresponding degrees of freedom. And to compute for your test statistic, you simply divide your mean square treatment by your mean square error. So now let's go back to our plasma etching data and look at the box plot and see where these things come from. So between treatments is the variation here, here, here. So basically for each, that's within treatment, okay. Between treatment would be between these individual treatments here, okay. And then your total treatments would be all over here, okay. So for all your data, basically. All right. So again, our example, we're interested in the response variable etching speed, or etching rate. We have the factor RF power. We have 4 treatments at 160, 180, 200, and 220. Okay, and we want to know whether there is a difference in the etch rate given these different treatments. Okay, so let's look at the worked out example in Excel. This is your data. Okay, we obtained here the totals, total observation for each treatment, and the average for each treatment. As you can see later, this will be useful. And the sum of all the observations. Okay, here this is just a matrix containing the square of each observation. Okay, this is the transpose of the totals per treatment. Okay, and I will be using that later, as you will see. So we pegged our alpha at 0.05. We have 4 treatments. We have 5 replicates per treatment. And so that makes for 20 total observations. Now to compute for your SST, okay, sum of squares total, this is basically the sum, okay, the sum of the squares of each square of each observation minus the square of the sum of all observations, that's G6, divided by your total number of observations. Okay, to get your treatment sum of squares, that's 1 over the number of replicates per treatment times the square of the sum of observations per treatment. And I just used here the matrix multiplication function in Excel for the sum of the observations per per treatment and its transpose. Well, this times this actually, minus the square of the sum of all your observations divided by the total number of observations. And this formula is basically from what I've shown you earlier. And your SSE is just the difference between your total sum of squares and your treatment sum of squares. Okay. Now we can summarize that in our ANOVA table. So we have 3 sources of variation. You have between treatments, that is the different levels of the power. Okay. You have the residual, okay, within treatment, okay, or error, and you have your total variation. And these are the sum of squares that we computed, and the corresponding degrees of freedom. For your treatments, you have A minus 1, so that's 4 minus 1. This is AN minus A, so that's 20 minus 4, 16. And then this is capital N minus 1, that's 21 minus 1, 19. And your mean square is just sum of square divided by degrees of freedom, okay, for each of these. Now your test statistic is basically your MS treatment divided by your MS error. So that's this divided by this, and we get 66.8. Now we compare that to F of alpha with degrees of freedom A minus 1 and capital N minus A. So that's F of 0.05, degrees of freedom 3 and 16. And I used here the function in Excel f dot rt, so inverse of the probability, and the probability is 0.05 with degrees of freedom 3 and 16. Okay, and I got 3.24. And our critical region is the region greater than this one. So now we test is F naught greater than this. And clearly 66.8 is much greater than 3.24. Therefore, we reject the null hypothesis. Alternatively, we can look at the p-value. So, using the F distribution, what is the probability of having this? This is, we can use here f.this.rt, okay? And our x here is f0, degrees of freedom 3 and 16, okay? And as you can see, the p-value is much less than 0.01, even 0.001, okay? Just for reference, if we compare this to a value of 0.01, we would have had 5.29 as our reference F value. Still, our F0 is going to be much greater than that. And so definitely, our p-value would be really, really low. If we just looked at this, we would still, of course, reject our null hypothesis. If we graph that, okay, this is our F distribution. We have the F values on the x-axis and the probability density on the y-axis. Our F0, computed F0, 66.8 is here. It's way to the right compared to our reference values at F 0.05. It's here. F 0.01 is here. So it's clear that we can reject the null hypothesis because our data does not support it. Okay. Now, we can also estimate the model parameters such as the treatment means as well as the difference in treatment means, okay, by using this formula. So it's the same process that we did in the previous hypothesis testing procedures that we discussed in previous lectures, and I encourage you to employ this formula and obtain the treatment means and the difference in treatment means for our plasma etching example. Now, these formulas are used one at a time. So you compute one treatment mean at a time or one difference in treatment means at a time. Now, I want you to research, okay, or actually just read from your book what Bonferroni method is. Okay, what is the significance of the Bonferroni method? When can it be used in relation to this? Okay? All right. So moving on, how about unbalanced data? So I already showed you earlier, or this talked about the difference between balanced and unbalanced data and the difference in the formula for the sum of squares. So far in our example, we dealt with the balanced data. Now, I'd just like to point out some advantages of balanced data and why you should aim for a balanced design in your experiments. One is that there is going to be a smaller deviation from the assumption that treatment variances are equal. And secondly, the power of your test is going to be maximized. But if you have no other option but to deal with an unbalanced design, then you know that you have the tools to analyze the experiment. Okay, so the next main topic is model adequacy checking. Now, the question here is, when can we consider ANOVA to be an acceptable procedure as an exact test of hypothesis of no difference in treatment means? Well, of course, we need to make sure that the following hold true. First of all, that you can actually use this model, this statistical model, to represent your observations. That is, y sub ij, your observation for treatment I, jth observation for treatment I is equal to an overall mean plus the mean of each treatment I plus error I sub j. Okay? And of course, that your errors are NID, normally and independently distributed, with mean equal to 0, and unknown but constant variance, sigma squared. Okay? So how do you check this? Okay? You can do this using residual analysis. And residual analysis or model adequacy checking is a must. Okay, so I will be looking for this section in your project, definitely. And I hope that you will always remember to do this in the future in your analysis, whether at work or in research. Okay, because you can't rely on your ANOVA without verifying that the model assumptions hold. Okay, so what is the residual? Your residual here, EIJ, okay, residual for observation J in treatment I, is equal to your observation J in treatment I. Okay, that's Y sub ij, minus the estimate of the corresponding observation Y sub ij. And how do you get the estimate for Y sub ij? Okay, this is basically equal to your estimated overall mean plus the mean of each of your estimated mean of each of your treatment. Okay, so this is equal to Y bar I dot. Okay, so again, what are the main assumptions? You have the normality assumption, you have the independence assumption, and you have the constancy of your variance. So your variance should be independent and constant. All right. So how do you check? For normality, you can use your histogram and see whether the histogram actually models a normal distribution. Or more effectively, more accurately, you can use, of course, your normal probability plot, which we have already discussed in previous lectures. And for the variance, you can do your residuals plot in time sequence and your residuals versus fitted values. Okay, so here you want to make sure that the residuals are not correlated. Okay, so that there should be no pattern when you plot your residuals versus time. Okay, and there should also be no structure or pattern when you plot your residuals versus your fitted values. So let's look at the normal probability plot for our plasma etching example. As you can see, the residuals are very close to our normal line. And so we can conclude here actually that the normality assumption holds true for our model. All right, now let's look at the variance. Do we see any pattern for the two graphs? The graph on the left is residuals versus time, run order or time. And then on the right, you have residuals versus the predicted values. The residual seems to be random, right? There's no specific pattern. So we can conclude here that we satisfy the assumptions on independence and constant variance. Okay. Now let's look at the following graphs so that you would be familiar with the behavior of residuals that are violating some of our assumptions. So let's look at this histogram. Clearly it doesn't model a normal distribution. Okay, if we look at the normal probability plot corresponding to this histogram, it would actually look like this. So if you see, you have your data and you plot, you have your normal probability plot and you see this, okay, you could conclude that your residuals are skewed and therefore are not following the normal distribution. Okay, so as in this case, it has a bell-shaped curve, but the tails are heavy. Okay, and if you look at the normal probability plot, it would look like this. This is a heavy-tailed residual distribution. So these two, they violate your normality assumption. Now let's look at this. This is the residuals versus your fitted data. And as you can see, the data is fanning out to the right. So there is a perceivable pattern to your residuals, which indicate that your variance is not constant, that your variance actually increases with increasing fitted value. Okay, so one assumption is violated in that case. How about this one? Residual versus fitted value. As you can see, there seems to be a pattern. From this point up to this point, your residual values are decreasing with increasing value of your fitted value. From this point to this point, it's the reverse. Okay? Still, there is a very obvious pattern. So, this strongly indicates that your variance is not constant. Now, how about this one? This is what we call positive serial correlation. As you can see, if we plot your residual versus time, there seems to be a pattern, positive, okay, serial correlation, okay, in your residuals. Your residuals are increasing over time, okay. So this means that succeeding observations are not independent from previous ones. Same here, okay. Same is true here, okay. It's like your residuals are reinforcing a pattern for the succeeding ones, okay. Now, this one is called a negative serial correlation. So, the observation following a previous one is the opposite. So, for example, here, you have a negative residual, and then you have a positive, and then negative, positive, etc. Okay, so this is a negative serial correlation. You also don't want this. Okay, it means that there is a dependence. There is a relationship between your observations. Okay, so if you encounter these situations, what can be done? One of the things that you can do is to first transform your data. Okay, and of course, if you transform your data, you have to remember to adjust your prediction model given the transformed data and interpret accordingly. Now, how about if you have an outlier? But first, how do you determine if you have an outlier? What you can do is use standardized residuals, and your standardized residual is computed as such. D sub ij is equal to your residual divided by the square root of your mean square error. Okay, and your residual, standardized residual, is normally distributed with mean 0, standard deviation 1, and what you want are residuals, standardized residuals that are within plus or minus 3 standard deviations. Now, anything beyond 3 or 4 standard deviations can be considered as outliers. What to do with an outlier? Okay, first, important that you investigate the cause. If it is non-statistical, then maybe you can discard it. But first look, is it particularly desirable or undesirable? Because if it is, then it can actually give you more information than the rest of the data. Now, if you're unsure what to do, at the least, you have to have one analysis with the outlier and another one without. Okay? Okay, so what are the implications if your assumptions are violated? For the normality assumption, if it is violated, then the true significance level and the power of the test are actually going to be different. And in general, your power will be lower. If you violate your independence assumption, this is a very serious problem and it has to be prevented at the design stage. Okay. Now, if you violate the constant variance assumption, your type 1 error and the confidence interval are going to deviate significantly from the true values. So, violations of your assumptions will actually render your analysis close to useless. So, you have to really make sure. Okay, or it could also provide you insight as to what you can do further to improve the experiment. But the bottom line is you have to always check for model adequacy. So, okay, so that's it for part 1 of our lecture. We have discussed the fixed effect model, and I hope you understood that. And then we performed some analysis of variance. We calculated sum of squares. And this is for our example, the plasma etching example. And then we differentiated between balanced and unbalanced design. And you know now what's the difference in terms of the treatment of the two. We were able to interpret ANOVA results, and we were able to perform model adequacy checking. Okay, so that's it for this lecture. In the succeeding lecture, we're going to talk about the extensions of our previous discussion, and that would be a discussion on random effect model. You have your randomized complete block design, you have your Latin squares, and you have your Greco Latin squares. Okay, bye for now.